So I'm going to talk about software compilation. I'm going to go a bit backwards again and say that you know that software written low-level languages such as C++ or Fortran, it needs to be compiled for it to be understood by the computer system. So it has to be compiled into machine code. So that's what the computer understands. And depending on which language you have, you have a different compiler to use. For example, we mentioned many times GCC. If you have something written. Oh, sorry. Thanks. There we go. Thanks. So this is a small table that shows you that depending on which language your software is written in, you can use a different compiler to compile your code so it will be understood by a computer. You can do that using a package manager that we mentioned many at this point. You can also do it manually without a package manager. I'm going to talk about that a bit at the end of this part. So first I want to show you two very short examples using Rust. So using Cargo package manager to install a Rust software and using Go to install a very small Go package. So before compiling something yourself in a cluster, there are a few things that you have to take into account. For example, compile on compute nodes. Maybe the thing that you want to compile is very small and it will not take a lot of computing power, but it's safer to do it in a compute node anyway. And also because if you're compiling something that it's architecture specific, so it has optimizations, you want to do it where you want to use the software afterwards. So if you want your software to work on a given partition, you better compile it in that partition if you're using optimizations. Second consideration, I think we mentioned this a few times, read documentation. That's very important. It will save you so much time, and most packages, most software have information on how to compile the source code. Sometimes it's well written, sometimes it's not, but it's always useful to give it a read the documentation. Third consideration is that we have in our sites a module called build-env, which can be useful if you're compiling code yourself, because it includes the compilers themselves, but also math libraries, MPI libraries, and also defines compiler and linker flags. So there are a lot of things that are already defined for you that when you're compiling that can be and most likely be useful for you when you're compiling the software. On top of that module, of course, you can use other modules that you might need, such as CMake or AutoTools or Ninja, any other modules that you might need. So it's a good idea for reproducibility to use this module. Okay, so first of all, this is a very small example of a Rust package called Dust. So if you want to compile this software yourself, you can use the Rust package manager called Cargo. So first of all, you will need the Rust module. You need of course, your source code that you can get with Git, for example, Git clone, and then go into the directory, select a version. It's always a good idea to work with versions instead of, to work with releases, so you can reproduce this very easily and maybe communicate what versions you're using. So once you have your code, you can get into the source code directory. and you can inspect what is inside. So I told you this is a Rust package. With Rust packages, you will have these files. Well, you will have many files, but you will have files called cargo.toml and cargo.log. Those are the files that Cargo needs for you to be able to use the package manager. So cargo.toml will have information about the software itself, the metadata, so the version, the name, the authors, dependencies. Then sometimes there is this cargo.log that will fix the versions of the dependencies of the given package. Sometimes this particular file is not present, but you can generate it with Cargo, and it's a good idea to do it so you can reproduce the installation if you need to, so you know which dependencies you used before. So that's it. You can use Cargo to build this with cargo build -- release, and this will create a binary. And this particular binary, it's under directory here called target release, and then you have the binary called dust. This binary needs an input, which has to be a directory, because it will the binary just, I mean, this software just shows the storage that is taken up by some files in a given directory. So it needs an input of a directory. So that's what I'm showing there on point 5. And that's it. So the binary is self-contained, and that's all you need to be able to use this Rust package. What you can do optionally, of course, is you can add this the binary executable to the path, so you don't have to execute each time by saying where the binary is. Good idea also to check which binary you're using, and if the export really worked. It's with this which command, which was already mentioned, I think. So it's a good idea to use it to check that you're using the binary that you want to use, if you have several versions maybe installed, and that it was correctly added to your path. That's about it for the compilation itself. So a two notes about this. First of all, that well, compiling like how I showed you before, so cargo build -- release will not optimize for a microarchitecture. It will build for a baseline architecture for a family of a CPU family, for example, x86. This will run on most CPUs. It is a good idea to optimize your the build, and that you can do with this Rust flags. So you can optimize it if you want with Cargo. But then again, you have to be careful of where you want to use this software. You want to compile where you want to use it. Another important consideration is you don't want to overflow your home directory. And if you do this without setting anything else, Cargo will by default make a hidden folder under your home directory, and will fill that with files. And you don't want that, because if you install a big package or many Cargo packages or Rust packages, this will fill up quite fast. So you want to either redirect this cargo_home variable to somewhere that has more space than your home directory, or you can symlink, so create a symbolic link from your home directory to, for example, VSC data, so you don't end up with a filled home directory. So for the Go package, it's very, very similar. You will need to also load a Go module. You will need to get your source code, of course. Again, you can maybe, depending on the package, do this with git clone. Select the version that you want to install. And then when you inspect the folder, you will have one or two of these files called go.mod and go.sum. It's basically the same as the cargo files. So go.mod specifies the dependencies, the module version, and the go.sum will tell you which versions exactly of the dependencies are going to be used. This go.sum will can be maybe it's not on the directory, and then you can create it just as like with cargo, which is also a good idea. It's recommended to do that. And then again, you can once you have the source code, you will use the command go build, and then you will specify you can specify an output directory. So that's where your binary will end up. And that's it. You will end up with a binary, and you will be able to use it. You can export the path again to be able to find the binary wherever you are, and that's it. Again, like the considerations that I talked about before for the Rust packages, Go does not have a microarchitecture optimization possible, so it will build for a baseline architecture. So it will run on more CPUs when you compile this. It would also, by default, store things under your home directory, which you don't want to do that. So you have to either redirect to two environment variables called go path and go cache, or you can symlink a directory called go and a directory under your cache in your home directory, and that's it. And then you will avoid flooding up your home directory. So that's quite simple to do. So now, what if you don't want to use a package manager, or you can't for some reason? You would need to think about maybe doing a manual software compilation, but you have to know that that's usually not a good idea because it's very complex and it's not easy. And if you don't have experience with that, it's going to be very challenging. And just to give you an idea, this is a very, it's a dummy example of how this would look like if you want to do it manually. For example, if you have, you would have source files, usually many more than just two, but let's say we have two source files written in C, and you want to compile this program. You will need to use the compiler, the GCC. It's usually a good idea to specify some kind of optimization, and this you can do with this -02, for example, depending on what level of optimization you want. And then you would have to compile each source code file. So this you have to do it manually, one by one. You will end up each time with a binary objects, and then you will have to link them together, and you will end up with a compiler, and then you will end up with a program that you can use. In this case, it looks simple. It's not. It's gonna be much more complicated than this. This example doesn't have any. You don't have to. I mean, usually you will have to link to external libraries, headers. This has no dependencies. Usually, you will have dependencies to handle. So that's why it's usually not a good idea to do this unless you really, really need it, or you know how to do it. Otherwise, it's a better idea to contact us. So between this and the package managers, there's a big difference. There are things in between that you can do. So you have automation tools that you can use. For example, there's make. Make is something that it has been around for a very, very long time, from 76. It's very, very old, but it's still very much used. Now it's very useful because it works with any compiler, any or language. It uses one file called makefile that is very easy to integrate into a project. And basically, this makefile, you can think about it as just a set of rules in a specific order that will tell the computer, that will run the commands in order to be able to end up with a working binary. It will handle then compilation, linking, and then installation. It can use system installed libraries, but it will fail if dependencies are missing. It will not install dependencies automatically. It will not automatically optimize your build, so you have to take that into account. A step further from this is to use a CMake. So CMake is a configuration tool. So it will configure your system. It will configure so you can build with another tool. It's also so it will, for example, generate a makefile that you can use to compile. It's also language agnostic, so you can use it with any language or compiler. And it uses a file called cmakelists.txt. And this defines how the project will be built. So it will do the configuration of the compilation, the linking, and the installation, and it can handle, of course, many source files. It will detect libraries, headers, and compilers. So for example, if there is MPI, then it will build with MPI support, for example. It can fetch or build missing dependencies, but this has to be specified in the CMake list file. And again, this will also not automatically optimize. You can pass flags optimization, but it will not do it automatically. So you have to be careful with that if you want optimization. So basically, what you need to compile software yourself is you will need a configure step if usually, and then you have to build with some tool, and finally install. So in this table, you can see that based on what files you can find on the directory, the source code, you will need to use a different tool. Okay, so for example, we saw that the CMake, if you see something with a CMake lists.txt, then you know that you can use CMake to create a make file, and then use make to build, and then you can use make install to install. If you see some kind of configure or configuration configure script, you can also usually run configure and then make install. We saw that with cargo, if you have a cargo.toml, or you can use cargo, and if you see a go.mod, you can use go. So basically, based on which files you find in the source code, you will be able to figure out more or less what tools you need. And each tool has you will usually need a module for that tool to be available on the cluster. Something that I didn't mention before, but it's here on the table, is that if you have a CMake lists, you can use CMake to create a makefile and then use make, but you can also use CMake and then specify the generator and use Ninja. So if you want to build with Ninja, for example. So I'm mentioning this because that's what I want to show later as a demo. But the conclusion of this slides is that building software manually, it's not straightforward. There are a lot of things to take into account that you need to know. You have to manage the dependencies, or at least know how more or less what the requirements are for the software that you're building yourself. You have to set up the environment correctly, and it's very easy for this to fail if unless the package is really simple. So it's a better idea to try to do either use package managers or contact us if you need a particular software. That being said, I wanted to show an example with GB Lite, and this I'm gonna do very quickly. Let's see. Okay. So here I am in our cluster at the VUB Hydra. I'm in a compute node, and if I want to then compile TB Lite, I will first. I should have done this. Get clone. I will first clone. Hopefully this will be fast. Usually it should be quite fast. And then go to the directory, and here it is. You can see you see a cmake list.txt. Let me just go to the version, select the version I want with the switch to the version I want to the 050. Yeah, and then I'm gonna try to compile with so I'm gonna use CMake, and I'm going to use Ninja. So that's why I'm going to load all these modules. So the build and the Ninja and CMake. And then I can build with sorry. So use CMake to first configure. So CMake, and then this -b is just going into the build directory. I'm selecting the Ninja, so I can compile with Ninja. And I'm just telling it where to install the software. I mean, where to put the build directory. Okay. That should work. And hopefully it will work. So, because I have only 3 minutes. Okay. So much faster when you don't do it in a presentation. Yeah, it's so.
This is a M5 node, so it's not slow.
I don't know. It should be fast. Yeah.
That should also be okay. Yeah.
So maybe.
No, but actually, if you want to know what is happening here, the CMake is basically doing all the detection stuff of everything that is needed by the software. It's looking at all the different places in the system, like where is this library, where is this compiler, does this compiler support this flag, does it not? And then it makes all these detections.
Yeah, as you can see, for example, found blast, for example, I found the library. Yeah, that's basically what it's doing. But yeah, it's done.
And it's also installing some of the dependencies.
Right. Yeah. Well, I don't think it's installed anything here, right?
No.
But it's detecting. I'm not sure.
I download some stuff, from GitHub,
Yeah, you're right. Yeah. But it should be then ready to build. Oh, sorry. I wanted to show this. So this is the directory that we have. And now we can compile with Ninja. It should also be fast enough.
This is also the type of effort we do when we install stuff centrally. So when we really try to compile things from source and keep an eye on how things are built to get good performance. We don't do it manually like this. We'll show you what tools we use for this. But this is why it takes sometimes a while to get something installed, because we really do the homework to make sure everything is working out well.
So here you can see it's building, right? It's compiling each of the files. Should be almost ready. I'm gonna stop here when if it doesn't fail. Yeah, okay. So yeah, you can also just install, and that also should be quite fast because just moving things around. Installing, and then we can export the path and which TB light, and there it is. There's TB light, and I have prepared just a very fast. So what I ran is just this. I just used TB light with a given test file that I had stored here, and that's it. That's how you build TB light yourself with CMake and Ninja. Yeah, that's it.
Any questions on this? Manual installation. Yeah.
Yeah, I know CMake quite well, but what's the difference between Ninja and CMake, more or less?
But Ninja, CMake is on it's configuring, and Ninja will build your software, right?
Yeah, okay. Great.
It's like a modern replacement for Make.
Yeah, okay.
Ninja is that's really sort of drop-in replacement for Make, let's say. Yeah, you can also do CMake build, but then it's really calling out to something like Make or Ninja for you.
Okay.
Yeah.
Sorry,
Basically an implementation tool. Another one. There are so many.
Yeah.
So my question was, if you now want to use the same compiled software on a different node, you have to recompile again?
It depends on the architecture of
Okay.
the node, right?
But it wouldn't be like out of the box. You can't just assume it will work on any.
No, you can't assume it will work.
Because this still is on your personal Scratch, I think. Is that? I mean, I'm just trying to understand what's happening. So it lives on your Scratch, but when you then go to a different cluster, it might fail.
Yeah, the Scratch is a shared storage, so you can access the same Scratch from all the compute nodes.
Mm-hmm.
So you generated a single binary. That binary, you can use it anywhere. Now, it will work or not, it depends.
Right. Okay. Yes. Okay. Great.
Right?
Yeah.
And if it will work or not, it depends on the hardware that you're using and how you build it. So, for instance, I don't know if you compile it with March native or
No,
not.
I didn't.
Probably not. No.
Okay, if it's not with March native or something that will optimize very hard for the hardware that you're using in your build machine, then it will be quite portable. But if you use something like March native that it's optimized for the hardware, then it will fail as soon as you go into CPU with a different microarchitecture.
So you have to be careful indeed. Yeah. In this case, it's probably fine because I guess out of the box, it will just build with a -02 compiler option, and you'll end up with a binary that will likely work across all AMD or Intel partitions. If you're trying to run that binary on an ARM partition, if there would be one on the same cluster, game over. There's no way it would work. And then if you use those specific compiler options, then yeah, it gets hairier. You'll get a faster installation, but a less portable binary. Yeah.
Having said that, also note on Rust and Go, the advantage of those is that the binaries that they generate are self-contained as well, in the sense that you have a single binary, but it can be used actually almost anywhere, because it will, in general, by default, they are not optimized, and they do not depend on anything external. So those are very easy to actually not even reuse, but you can just copy the binaries to some other system or some other location, and it will work. While in this case, if you move the binary to a different location, it might actually break. Just because it cannot find the dependencies that it needs, like the external libraries and things like that.
Yeah, should we get into static linking or not?
Well, that's really works, yeah, but yeah.
Yeah, but you cannot, in principle, often also do static linking.
Yes, but,
and then it becomes more portable in the sense that the libraries that you're using are also included in your executable, which then gets quite large.
Yeah.
Maybe that's too advanced. Another very advanced thing is that in principle, it's also possible to compile for multiple architectures at once. And then at runtime, automatically the optimal instructions will be selected.
Yeah.
But I think that generally we recommend to compile on the architecture where you're going to run it, and then optimize it for the architecture where it's compiled. I think that's the easiest approach, right? Mm-hmm. But you can make things more complicated for yourself.
Complicated or better or bigger or more flexible. Yeah. There's lots of options. Okay. I think we're good to switch to the next part before we have a coffee. Is it coffee break already?
It's coffee
yeah, okay. Yeah. Let's do coffee break first. And then there's 2 more parts after the coffee break.